Hello, this next video will show you how to run parameter estimation in Copasi. Let's go ahead and open the 9-node model, and you'll find parameter estimation under the task menu here on the left. Now, what is parameter estimation? Parameter estimation is a process where you get to give specific values to your parameters of your reactions. There are two big challenges in building a network. One of them is finding those parameters, and the second is to find the experimental data to get those parameters right. One of the things that I want to show you today is, one, how a calibration database should look like, and two, how you would use that database to run a proper parameter estimation with Copasi. So let's get started. Here on the left upper part, I have this file. It's a database that I just constructed, and it's a calibration database. If we open that with Excel, I can show you how this is oriented and coordinated. All right, the first row that you can see here are the 9 species of the model, and each species has 3 different values. We have IL-6, TGF, and IL-12, and then we have TBET, ROR, gamma T, and FOXP3 as our transcription factors, and also we have our interferon gamma, our IL-17, and our IL-10 as our cytokines. We also have our inducers. IL-6, do you see this 0? That's the initial concentration of IL-6. And we have 3 different situations here. Let's take a look at these 3 different situations. The first one, you'll see that there's a 3 on the IL-12. There's an amount of 3. The concentration is 3. Therefore, T-beta and interferon gamma will get activated. 0 will be the number on the other ones. The second case is a Th17. We have 3 and 3 in IL-6 and TGF-beta. ROR, gamma T, and IL-17 will get activated. The third case or experiment is the Treg activation. We just have TGF-beta, and therefore only FOXP3 and IL-10 will get activated. Now, this calibration database is extracted from experimental data, and this is something you'll need to consider when constructing your model, how you are going to calibrate your model. And maybe while the parameter estimation runs, we can maybe discuss a little bit more how we can approach these problems and how we can find different strategies to make this really hard task an easy one. But for now, we can go back to Copasi maybe, and I'll show you how to implement this database in the software. All right, so here we have the parameter estimation task. If you check this upper button here, it says experimental data. If we click in there, a new dialog will open. This dialog will allow us, the users, to upload our experimental data by clicking that plus sign here that you guys have on the screen. Now, if we select the file and we click open, now you can see how the software Copasi read our txt file and automatically populated these species here. So we have the 9 different species, and Copasi automatically detected that this is steady state. If we had time course data, probably Copasi would have put time course in there. But anyway, we have our 3 different species, and all of them are in the ignored type. And we have 2 options here. We can select independent, or we can select dependent. In the first case, independent will go with species that do not change over time. So they are independent. Dependent, on the other case, are species that will change because of a reaction has been activated. IL-6, TGF-beta, and IL-12 are our inducers. Therefore, the class, the type they have, they will be independent. When we click independent, you will see that there's this other dialog that opens, and we will be able to select IL6. And what we are doing here is to map each column on the experimental file with a specific species of the model. We are mapping the file, the experimental data, with our model. We'll go ahead and do the same thing with TGF-beta and IL-12. We'll select independent, we'll select initial concentration, and then we'll select, in this case, TGF-beta, click OK. Same thing, we'll do exact same thing for IL-12. Independent, select the initial concentration of IL-12, select that, click OK, that's it. Alright, so now we have our inducers all set up. Let's take a look at what happens here. See this Copasi sign? You can click on the Copasi sign and change the mapping you've done. In this case, we've done it correctly, so we don't want to change it. The other 6 species will be dependent, and the reason why is because as the induction happens, this species will change its concentration because of different reactions that are being activated in the model. In this case, instead of initial concentrations, we'll select transient concentrations as I am showing you guys on the screen. We'll select species, transient concentrations, and then we'll select the exact node that we want to map. For Tibet, we selected Tibet. For interferon gamma, we selected interferon gamma, and so on. And we'll follow the same rationale for all the 6 species. As you can see, there is different columns in this dialog. The last one is named weight. Copasi will apply a random weight based on how our model is set up. But this is something that you really don't need to worry about. It would be in a more advanced level when you want to change the weight of different species. For now, I would just keep it like that. Last one, IL-10, species, transient concentrations, select IL-10 over here. Okay, perfect. So this is how you implement your data, your experimental data. We have our species, 3 inductors that are independent, 6 other species that are dependent because they change. We mapped these columns to objects in the model, and Copasi assigned different weights that, as I said, we really don't need to worry about now. All right. Once we are sure that everything's okay, we'll press OK, and we'll go back to the first dialog. Alright, here we have our objects, and here we need to select which parameters we want to estimate given this experimental data. If we open the reaction parameters, we can select all the parameters. If we highlight reaction parameters, we'll select all of them. Okay, let's select all the parameters here, and you can use the button Shift on your keyboard to do so. And then we'll change the lower bound and the upper bound. This limitates exactly the bounds of your parameter. If we put 0.1 and 1, your parameter will never be less than 0.1 and will always be no more than 1. So you can see that here. Now the star value. I like to start in random values. You are eliminating a lot of bias if you start just giving random values. Alright, now that we have everything set up in here, I want to make one quick note. This is a model that is initialized using different combinations of cytokines. Before running parameter estimation, we need to make sure that the model is not initialized on a specific phenotype, because if we do it that way, we are favoring a phenotype. So let's put all the initial concentrations at 0 and go back to parameter estimation. Here we set up the values. Here we are selecting the algorithm. Now there are several algorithms that you can run parameter estimation with. If you go to copasi.org, you'll find a lot of documentation on what is each algorithm and what is used for. I mainly use 2 algorithms, particle swarm and genetic algorithm. And I can, once the parameter estimation runs, I can explain to you why. We'll leave the iteration limit at 2000. And again, I want to highlight the function of the output assistant. If we click the output assistant, we can get these plots here that I already pre-made, the parameter estimation result, those are the curves, and then we will also select the same parameter estimation results but by experiment, just in case. Most probably these plots are going to be the same, but sometimes depending on your setup they can be different. So we'll just select both of them just in case. Once everything is good to go, we'll press run. And this new dialog will open. Now you see parameter estimation is a task that will take a little bit more time than other tasks. With a 9-node model with so many parameters, it will take a little bit of time. We can pause and stop the task at any time. Copasi offers you this flexibility and this option. And then here we have the best value. What Copasi is trying to do is to minimize this best value by evaluating different functions. I don't want to get too technical here, but if you're interested in learning more about how this algorithm works and how Copasi evaluates this function, again, there's plenty of information at copasi.org under documentation, so feel free to go and explore. As I was saying before, and now this task is running, and I'm going to take advantage of this time to just talk a little bit about parameter estimation. As I was saying before, when you create a big model, you have the problem, you have the challenge of calibration data. Just think it like that. A model that has 3 nodes, it's pretty easy to select the parameters and make it work. A model that has 9 nodes like this one, for example, where you have 3 different phenotypes in this case like Th17 and Treg that interact between them, ROR gamma T inhibits FOXP3, FOXP3 inhibits ROR gamma T. We are dealing with these interactions. Therefore, having a good parameter set is key if we want our model to mimic our experimental data. And this is why parameter estimation comes in extremely in handy. What Copasi is doing right now is evaluating your experimental data and tweaking these parameters up and down to find a result, a parameter set that will represent your experimental data. And you may understand this a little bit better as we look at the results. The second thing I want to highlight while this task is running is the need for calibration data. Time course analyses are always better for calibration purposes. Now, the bigger the model, the more data you'll need for experimentation, for calibration. On this note, it's very, very useful if we can take advantage of different strategies to gather this calibration data. And this is why, and now you're seeing this video today, tomorrow we're going to be showing you another approach you can use to analyze your data and then use that data for this exact same task that we are running right now, which is parameter estimation. Also, 2 days from today, we're going to be learning about IPA, and also sequencing data, microarray data also offers you a lot of experimental data, expression data to calibrate your model. So as you prepare your experimental studies, just keep this in mind. Keep in mind that you're going to need a data set for calibration of your model. And then once you run your in silico experimentation, once you generate your hypothesis, then you're going to need to run another experiment to validate this hypothesis, as we were highlighting in the morning. Perfect. So these are just 2 minor things that I wanted to highlight just to make sure we're on the same page. But going back to the parameter estimation, here if you were looking at the screen, you may have seen that the best value is actually getting smaller and smaller and smaller as the functions are completed. This is about to get done. We'll wait a couple seconds for this to finish, and then what we will do is dive directly into the results. Okay, done. We get a message here. It's just a warning. It's not something that you really need to worry about, and it says that the Fisher information matrix is singular. This happens when your model has linear dependencies. There's a part of the result that will create a matrix. but that's okay. If you don't get that matrix in there, that's not critical, so that would be okay. All right, let's close the plots that we don't need, and these are the two plots that we created with the output assistant, which actually they turn out to be the same. So let's just look at one. And this now may look confusing, but I'll show you how to interpret that. All right, we have three different values here. We have a measured value, which is our experimental value. In this case, we have 1, 2, and 3 values, at 0, at 1, and at 2. See, we have the 0 here, we have the 1 in here, and we have the 2 in here. And again, this is the measured value, the experimental value. Let's take a look at the database real quick, and you'll understand why there's 3. See these 3 rows, 1, 2, and 3. There are 3 different experiments. The first experiment falls in here, the second experiment falls in here, the third experiment falls in here. Copasi will just create a line between them, which is not really important. But let's say TVET, we have an upregulation of TVET in the first experiment, and do you see this fitted value here? This fitted value is the value that Copasi is able to fit, tweaking the parameters of your model. So the result is something that, see, it's around 0. The weight error, if it's around 0, then it's a good sign. Again, measure value versus fitted value, experimental value versus the computational value that Copasi has found. Do you see how it's very close? And the error is very close to 0, which is great. Maybe you will understand the error once we go to the numeric values in the other part of the result. And here what I'm doing now is checking that the measure value, my experimental value, and the value that Copasi has been able to fit are on the same place, or they are close enough for me to consider that that was a successful parameter estimation. From what I can see on this plot, this parameter estimation ran really well. All the weighted errors are around 0, which is good. And then the measure value and the fitted values are pretty much falling under the same coordinates. So this is great. Weighted errors around 0, that's great. IL10 is the last one. Fitted value, measure value, perfect. So I would say by just looking at this plot, this parameter estimation has worked. Sometimes you'll see how parameter estimation did not work. Then it's just a matter of running another algorithm, running it maybe longer, or changing your experimental data, or even your model. Let's take a look at the numerical results. See how this standard deviation of the overall result is very close to 0? There's not a lot of deviation from the fitted values with the experimental values. If you want to go parameter by parameter, really like down to which parameter has like a greater deviation, you can do so. Overall, the experiments have a very low standard deviation, which is good. These are the fitted values that we've been able to fit. And this is what I was saying about the correlation. Let's go back to the correlation. This is this Fisher matrix that could not be calculated because our model has linear dependencies, but that's fine. This is not the matrix, but this is the Fisher information. So here what it's telling us is the relationship of different parameters. If you want to spend time taking a look at that, for example, here it's telling us that the K1 activation of TVET has a negative correlation with the K1 degradation of interferon gamma. There are a lot of parameters that you can assess in here, and as you can see, you can scroll. Let me check. You can scroll here on the right, yes, and there's a lot of parameters that you can check. What's most important is that the parameters are fitted, the standard deviation is low, and that the fitted value falls on the measure value or the experimental value. Now take a look at these reactions. Remember how we set up all these values at 0.1? Well, this is 0.04. But now, if we go to update model here, these values have been updated. So what Copasi has done is all these values that were 0.1 before, now it has updated all these values here. And now our model should work. Let's take a look if it works actually. Let's initialize the model with TGF beta and IL6, and we'll run a time course. We'll click running here. These are the plots for the Premier estimation, so we'll close them. Okay, perfect. This is the time course. All right, can you guys observe how ROR gamma T and IL-17 are up? And if you check the other ones, all of the other ones are downregulated, which makes sense, right? We are initializing into a Th17 phenotype. All of them should be downregulated except for ROR gamma T and IL-17. Let's take out the IL-6. Let's set IL-6 to 0. And what we will do is go to the time course and run it again. Okay, we'll close again these plots. And can you guys observe now that ROR and IL-17 now are 0, but FOXP3 and IL-10, they are upregulated at the levels of our experimental data. Alright, the last phenotype we need to check is Th1, which is an independent pathway in this model. Put IL-12 upregulated with a 3, we'll run it, and as you can see, now TBET and interferon gamma are upregulated. And the other molecules, the other nodes in this network are downregulated. Th1 does not have ROR gamma T or FOXP3 or IL-17 or IL-10. Great. Let me give you a little tip here with the plots, because I'm seeing here that some plots are coming up. If you go to, there's an option of output specifications, and you can actually activate or deactivate the plots that you want to show when you run a task. See, I'm deactivating this tree and running the time course again. And now the other plots are not coming up, just the time course. Just a little tip. All right. Here, this is how Premier estimation works. There's more stuff. You have the numerical results. Here, if you want to learn more about Premier estimation, please feel free to go to copaci.org. But for all terms and purposes of what we're doing today, this would be a very complete overview of Premier estimation.